The Territorial War, at the end of which Canada and the USA will emerge as two of the biggest losers. Link and Hinkle, in their study Coastal Migration Due to 21st Century Sea Level Rise, quantify the projected cumulative land loss due to sea level rise for Canada and the USA as 23,400 and 15,200 square kilometers, respectively. The minimum and maximum estimates vary substantially, ranging from 8,000 to 43,900 for Canada and 8,100 to 39,000 for the USA. These figures underscore the significant vulnerability of both nations' coastlines to a changing climate. To put these losses in context, Ukraine is estimated to have lost about 115,440 square kilometers of territory since Russia's initial 2014 invasion. Projections, meanwhile, indicate that Russia may face the highest median land loss from sea level rise this century at 28,600 square kilometers. These comparisons underscore the complex geopolitical and environmental stakes involved. These vulnerabilities are grounded in measurable changes. Since 1880, global sea levels have risen by approximately 20 to 23 centimeters, primarily due to the melting of glaciers and ice sheets, as well as the warming of the oceans. Not only is this rise accelerating, but in 2023, the average sea level was 10 centimeters higher than it was 10 years prior. Looking back at paleoclimate records, sea levels were 6 to 9 meters higher than they are today during the last interglacial period, which was only slightly warmer than the present. This comparison helps put the current trend into perspective. Projecting forward, if sea levels were to rise by 9 meters, the United States could lose between 202,500 and 270,000 square kilometers of land. Russia might lose between 112,500 and 157,500 square kilometers, and Canada could lose between 58,500 and 90,000 square kilometers. This would mean the USA could lose up to 2.95% of its land, Russia up to 0.96%, and Canada up to 0.90%. These numbers illustrate the potential severity of the long-term effects of sea level rise. The time frame for reaching a 9-meter sea level rise depends on future emissions. With a low emissions pathway, this could take 3,000 to 10,000 years or may never occur. A moderate emissions scenario could result in such a rise in 2,500 to 4,000 years. If high emissions continue, as are currently being observed in Russia, the US, and Canada, this rise could occur in just 200 to 600 years. This highlights the significance of contemporary policy decisions in safeguarding coastlines for future generations. The rate at which the ocean absorbs heat is a crucial indicator of Earth's changing climate. The ocean absorbs more than 90% of the additional heat generated by greenhouse gas emissions from human activities. This makes the ocean a crucial factor in regulating global temperature and monitoring global warming. Ocean heat uptake also affects the climate's sensitivity to changes, helps us predict future climate trends, and has lasting effects on ocean currents and sea levels. Since 1850, the global average temperature has risen by about 1.5 degrees C. The ocean's upper 200 meters, the mixed layer, however, has warmed by 0.6 degrees C, accounting for 7% of the total ocean warming of 0.042 degrees C. The thermocline, located between 200 and 700 meters, warmed by 0.3 degrees C, accounting for 13%. The deep ocean, 700 to 2,000 meters, warmed 0.1 degrees C and contributed 30%. And the abyss, located below 2,000 meters, warmed by 0.02 degrees C, accounting for approximately 50% of the total ocean warming. This thermal stratification arises from differences in temperature and density, which trap heat and carbon dioxide at the surface, resulting in a distinct layering of the water. This process contributes to atmospheric warming and amplifies the feedback on sea surface temperatures. It also restricts the vertical movement of nutrients and oxygen, thereby reducing the productivity of marine ecosystems. Nonetheless, the stratification allows for the conversion of tropical ocean temperatures as high as 38 degrees Celsius, such as those recorded in Florida in 2023, in accordance with the first and second laws of thermodynamics. The ocean thermal energy conversion process, particularly the deep-water condenser version, not only generates work, but also delivers residual heat to a depth of 1,000 meters. This heat returns at approximately 4 meters per year and can be recycled up to 12 times until all warming energy is converted and dissipated to space. Seawater expands differently depending on depth as a consequence of a property known as the thermal coefficient of expansion. At the surface, seawater's expansion is twice as much as at 1,000 meters. So, if heat is stored at an average depth of 500 meters, the resulting thermal expansion would be about 25% less. More importantly, this deep stored heat would not be able to melt ice sheets or glaciers, which currently account for around 21% of recent sea level rise. The heat generated by global warming can be converted into over twice the energy currently derived from fossil fuels, and at a much lower cost, excluding the $7 trillion in environmental costs estimated by the IMF for burning fossil fuels. This represents a baseload resource, with costs approximately one-third of those for solar power, providing 4 hours of backup, and 40% of those for wind, with the same backup. When factoring in a sea level mitigation incentive of at least 25 cents per kilowatt hour, this form of energy would have an effective negative cost